Good day, students. In our previous lecture, we have seen about RISC architecture. RISC stands for Reduced Instruction Set Computers. We have also seen about the different characteristics in RISC architecture. So, under RISC, we have three different types of architectures: PowerPC architecture, UltraSPARC architecture, and Cray T3 architecture. So, in our last class, we have seen about PowerPC architecture. PowerPC architecture is actually introduced by IBM. So, today, in our today's class, we are going to see about UltraSPARC architecture. Under RISC, UltraSPARC architecture. So, this UltraSPARC architecture is announced by Sun Microsystems in the year 1995. SPARC. So, SPARC family. So, SPARC stands for Scalable Processor Architecture. So, this SPARC architecture has wide range of applications. It is suitable from micro to supercomputers. So, SPARC first introduced model is SPARC, then they have introduced SuperSPARC. So, later on they have introduced UltraSPARC. So, now currently a lot of versions are available. So, these three models are upward compatibility. They have been developed with upward compatibility. So, but these three architectures share the same basic structure. So, now let us see about the different hardware features available in UltraSPARC architecture. So, the first hardware feature is memory. So, coming to memory, all are byte addressable. Two consecutive bytes form a half word. 4 consecutive bytes form a word, and 8 consecutive bytes form a double word or D word. So, the alignment: half word are stored in memory beginning at byte addresses that are multiples of 2, whereas words begin at addresses that are multiples of 4, and double word begins at addresses that are multiples of 8. So, the format for data storage is, so UltraSPARC supports Big Endian format. So, under Big Endian format, the MSB bits will be stored in lower addresses. For example, if this is our word, so this is our MSB and this is our LSB. So, if this is our memory, so this is the starting address A, this is A plus, this is A plus plus, and this is A plus plus plus. So, likewise I have increased by memory architecture from lowest address to the higher address. So, under Big Endian format, the MSB bits, that is 0x, is stored in the lowest address, then 0A is stored in address A plus plus, then 0B is stored at address A plus 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 and 0C is stored at address A plus plus plus. So likewise, the MSB bits are stored in lower order address. That is the format for big Indian format. Here in UltraSPARC architecture, we are having virtual memory space. So the virtual memory space is of about 2 power 64 bytes. So our UltraSPARC programs can be written using 2 power 64 bytes of virtual memory. During execution, these conversion, that is the logical memory, so during execution, the data stored in the physical memory has to be converted to the logical memory. So that will be done by the memory management unit of the operating system. So that's all under the hardware feature, memory. Next is registers. More than 100 registers, general purpose registers are available in UltraSPARC architecture. But any procedure can access only 32 registers. Registers starting from R0 to R31. So any procedure can access only 32 registers. In that 32 registers, first 8 registers R0 to R8 are global registers. That is, they can access by all the procedures of the system. R0 will always hold the value 0. Other 24 registers. Other 24 registers can be visualized as a window through which part of the register file can be seen. For example, if R8 to R15, so if this registers is used by calling procedures, then R24 to R31 will be used for called procedure. So both of these registers will contain the same data, but while during procedure call and during procedure definition, we may use different kinds of attributes. So in order to hold that attributes, we will be using different kinds of registers. So R8 to R15 will contain the variables of calling procedure, and R24 to R31 will contain the data of called procedure. We are also having program counter register. So program counter register will always store the address of the next executable register instruction. Then condition code register. So condition code register will always stores the result of the condition, and floating point unit is there, and other control registers are also present. So totally more than 100 general purpose registers are available in UltraSPARC architecture. So our next hardware feature is data formats. So integers, under data formats we will be seeing about integers, floating point, character and negative values. So integers are represented in 8-bit, 16-bit, 32-bit or 64-bit binary numbers. Then for storing negative values, we will use 2's complement method. Character is stored in 1 byte ASCII code. So it supports both Big Endian and Little Endian ordering. three different floating point formats are there. Single precision, double precision and quad precision. So, under single precision, it is of 32 bits long, that is 23 for storing the fraction numbers and 8 for storing the exponent and 1 for storing the sign bit. Then double precision, so double precision is of 64 bits. So, 64 bits is segmented into 52 for storing fraction number and 11 for storing exponent and 1 for storing the sign. Then quad precision. So, quad precision, under quad precision format we can store floating point numbers of 78 bits long. So, 78 is segregated into 63 for fraction and 15 for storing the exponent value. So, that is all about the data formats. Next, let us see about instruction formats. UltraSPARC architecture supports 3 instruction formats. So, all the instruction formats are of 32 bits long. So, under instruction format, first 2 bits will identify the formats, which format is used. So, format 1 is for call instruction, format 2 is for branch instruction and format 3 is for all the remaining instructions. All the instructions are of fixed length. So, we have already seen in RISC characteristics, all the RISC machines will have the fixed instruction length. Since we are the instruction length are of fixed, the execution speed will be very much increased. Next, addressing modes. So, UltraSPARC architecture supports the following addressing mode. Immediate mode. So, under immediate mode, the value of the operand is represented in the instruction itself. Then register direct mode. So, under register direct mode, the value of the operand is present inside the register. Then memory addressing, here the value of the instruction, that is the operand, is present and resides inside the memory. Load and store operation will be used for fetching the values that is present inside the memory. Now, let us see how to calculate the target address for each addressing mode. If the addressing mode is program counter relative, PC relative, the target address is calculated as the content that is stored inside the program counter plus displacement value. So, this is of 20 bits and signed. Register indirect with displacement. So, here the target address is calculated by the content that is stored inside the register plus displacement. So, this is of 13 bits and signed. Then register indirect indexed, indirect and indexed. So, in such case, the target address is calculated by register minus 1, the value that is stored inside the register minus 1 plus the value that is stored inside the register minus 2. The sum of both the result will be the target address. So these are the different addressing modes available in UltraSPARC architecture. So always a PC relative addressing mode refers to memory addressing. So this is used for branching instructions. Next, instruction set. So under instruction set, we are having more than 100 instructions. So the execution of instructions are pipelined execution. Pipelined execution is nothing but while one instruction is executed, the next one is fetched from memory and decoded. In order to increase the efficiency of pipelined execution, we will use delayed branches. So delayed branches is nothing but the instructions immediately following the branch instruction is actually executed before the branch is taken. And also we are having special purpose instructions also. So special purpose instructions are used for doing some special functions like high bandwidth load and store operations, and special atomic instructions are also there to perform the work of the processor. So that instructions comes under special purpose instructions. So that's all about instruction set. The last hardware feature is input and output. So under input and output, so the communication with I/O device is accomplished through memory. So in memory, we are having a range of memory locations which is logically replaced by device registers. So that portion in memory is called as I/O space. So each device, I/O device, will be represented by a unique address. So when load and store instructions refer to this device register that is present inside the I/O space, the corresponding device get activated. So no special I/O instructions are needed for performing this I/O. See, for example, if this register R1 is meant for the device, input device, keyboard, and if the register R2 is meant for the device mouse. So by loading or storing the data from the keyboard to this particular R1 register, this keyboard will get activated. While while performing load and store operation in this register R2, the device mouse will get activated. So likewise, input and output operations are performed. So in our today's class, we have seen about the different hardware features in UltraSPARC architecture. In our next lecture, we will be going to see about the next architecture in RISC, that is Cray T3E architecture. Thank you.